Our goal is to understand how the properties of the elements are related, how a chemist can predict element properties from the position of the element in the periodic table, and the underlying reasons for the observed trends. As you learned in another Go Chemistry module, the 19th century Russian chemist Dmitry Mendeleev is largely credited with developing the modern periodic table by organizing it around observed trends in the chemical and physical properties of the elements. Now we would like to look at some of the properties of those elements and understand more about the underlying reasons for the observations. Before discussing periodic trends, there are two things we should touch on. First, you should review electron configurations and how those are related to the position of the element in the periodic table. Second, we should touch on effective nuclear charge. The effective nuclear charge is the charge actually experienced by an electron in an atom. It is essentially equal to the nuclear charge as modified by the effect of the other electrons in the same shell and in inner shells. Let's look at the graph on this screen. There are two important points to make. First, the effective nuclear charge experienced by the outermost electron increases as we proceed across the period. Second, consider lithium as an example. The atom has 3 protons in the nucleus and 3 extranuclear electrons, arranged as 1s2, 2s1. The effective nuclear charge experienced by the 2s1 electron is slightly greater than 1. This tells us that the 2 1s electrons do not entirely block or screen the +3 charge of the nucleus. So the charge effectively felt by the 2s1 electron is slightly greater than 1. Let's examine the atomic radii of the elements relative to their position in the periodic table. Again, there are two important points to examine. First, atomic size clearly decreases on going across the periodic table. The reason for the decrease is that the effective nuclear charge increases across the period. Moving down a given group, the size increases because electrons are being placed in electron shells further and further from the nucleus. The ionization energy of an atom is the energy required to remove an electron from that atom in the gas phase.
To remove the outermost electron from a magnesium atom requires 738 kilojoules of energy per mole.
Periodic trends in ionization energy are directly related to those for atomic size. Moving across a given period, the ionization energy generally increases owing to the increase in effective nuclear charge. Moving down a group, the ionization energy generally declines. The underlying reason for this is that the electrons are being placed further and further from the nucleus, and so the effect of the nuclear charge decreases. It is interesting to look at the trend in ionization energy in just a bit more detail. The increase in ionization energy across the table is not nicely linear. For example, the ionization energies of boron and oxygen are just a little lower than we might have expected. The underlying causes of this are related to their electron configurations and give us some insight into the details of atomic structure. The electron being removed from the boron atom is a 2p electron. The 2p orbitals are slightly higher in energy than the 2s orbitals, so less energy is required to remove the 2p electron of boron than to remove one of the 2s electrons from beryllium. Oxygen represents another interesting case. The electron being removed when oxygen ionizes is one of a pair of electrons. The electron-electron repulsion effect causes this configuration to be lower in energy than that of nitrogen, and thus oxygen ionizes at a lower energy than does nitrogen. A number of atoms take on electrons to form anions. We can measure the ability of an atom to acquire an electron with the electron affinity. The electron affinity is defined as the energy released when an atom in the gas phase acquires an electron.
When a gaseous atom accepts an electron to become an anion, the energy it releases is a measure of its electron affinity. For chlorine, this is minus 349.0 kilojoules per mole.
In general, the affinity for an electron increases as we go across a period. We see this because the energy released, the electron affinity, increases as we go across a period. The underlying reason is once again the increase in effective nuclear charge as we go across a period in the periodic table. Moving down a particular group, the size of the atoms increases, electrons must be added further and further from the nucleus, so the attractive force between the electrons and the nucleus decreases. As in the case of ionization energies, these trends are not nicely linear. There are always some anomalies, and these are really quite interesting. You should see your textbook for some more details. Periodic trends we've discussed will help us greatly to understand some of the chemistry of the elements. For example, sodium in group 1A has a relatively low ionization energy and so forms a sodium +1 cation. Sodium could lose a second electron to form an Na2+ ion, but the second electron would have to come from the N=2 shell. This requires a much higher ionization energy, so sodium typically forms only the Na+1 cation. Chlorine atoms have a relatively high affinity for electrons, and so readily form Cl- anions. All of this means that sodium chloride has the formula NaCl, and not something like NaCl2 that would imply a sodium 2+ cation. The chemistry of the elements can be predicted and understood by looking at the periodic trends in the physical properties of the elements.